Okay, in this presentation we're going to look at the binomial distribution, okay? Now it doesn't really specify it there in the question that it is the binomial distribution, but we'll sort of come across it soon enough. During a promotional campaign of a new soft drink company, the company places prize winning caps on one of every 10 bottles. Okay, let's highlight that part there. Okay, so the probability of a success is 1 in 10, and a prize winning is the success, that you win a prize. That's our success. So we're starting to feel it's a binomial distribution already. Hoping to win a prize, a child decides to buy a bottle of the new drink each day for 1 week. Okay, so what is the probability that the child will win some prizes? Okay, so again, we have a week there, so 7 days. So there's 7 trials. Okay, so each day, that's our trial there. Try a bottle of the new drink each day for 1 week. That's our trial, and it's the number of trials. Okay, so 7 days. So it's pretty much set up as a binomial distribution. So x is binomial with n equal to 7 and p equal to 1 in 10. Okay. So you just something like that has to be just specify it. Just actually spell it out and sort of justify it from the question. A little sentence or two just to justify from the question. So this is the questions we're asked. None of the days, at least 1 day, at least 2 days, and each day. What is the probability for each scenario? Okay. Now, so this is a bit of theory. This is essentially lecture notes, essentially. Okay. The important thing here is actually, first off, I should just sort of make mention of the fact that this does not do exclamation marks very well, this formatting system. So the exclamation marks go missing. So it's n factorial over k factorial times n minus k factorial. That's our choose operator, binomial coefficients. Okay. So these are the key things you have to need to know here. Okay, this formula here, this is the probability mass function. The probability of getting exactly k successes in n independent trials is given by this formula here. So essentially, this part here is what we're going to rely on. Okay, and if you're unfamiliar with this part here, it's the binomial coefficients. Okay, the choose operator, in other words, and so just a sort of bit of practice with that expression there as well. It's straightforward enough, really, but those are the two key building blocks of the question that we're going to do. Well, we'll also need some lateral thinking in a while, shortly as well. Anyway, so so there it is, just a sort of statement there. Now, q equals 9 over 10. So the first question is, what's the probability that the child does not win any prizes at all over the course of the 7 days? So n here is 7, and in this instance k is equal to 0. Okay, so we're going to use our formula there. 7 choose 0. Okay, now if you're unfamiliar with this, just as a quick remark, 0 factorial is always equal to 1. Okay, if you're not sure of that yet. Okay, so when you calculate this out, didn't mean to do that. When you calculate this out, the 7 choose 0, it should end up as 1. Okay, 7 choose 0 is equal to 1. Now it's 7 factorial divided by 7 factorial times 0 factorial. So 7 factorial divided by 7 factorial cancels out to 1. Okay, also just to sort of also remark upon the fact that we have 0.1 to the power of 0. Anything to the power of 0 is 1. And finally, 0.9 to the power of 7. So essentially this reduces to 0.9 to the power of 7, and that gives us 0.4783. So that's the answer to our first one. Okay. The second question is at least 1, more than 1. Okay. Let's just double check what the question is. Yeah, at least 1 day the child wins a prize. Okay. So there's a little bit of lateral thinking here. We don't have to do too much, but essentially just to note that at least 1 is the complement of winning nothing, no days. Okay, so at least one day the child wins a prize. So essentially what I'm doing here is just getting the complement of this. So this is 1 minus 0.4783, which is the answer to part A, and that gives us 5217. Okay? Then the third one is exactly 1. Okay? And that is 7 choose 1 times 0.1 to the power of 1 times 0.9 to the power of 6. Now this is done more or less the same way as part A, okay? Just rather than 0, we have 1. Okay, 0.1 to the power of 1, that gives us 0.1. 0.9 to the power of 6, that gives us 0.53144. And 7 choose 1 is 7 factorial over 6 factorial times 1 factorial. The 1 factorial cancels out, okay, just 1. And 7 factorial can be written as 7 times 6 factorial. They cancel out, so that just equals 7. Okay, so that's where that 7 comes from. So a little bit of calculator work, okay, and we find that the answer is 0.3720. Okay, so what's the question actually? Sorry, just what is the question here? At least one day. Okay. No, at least 2 days. Okay, sorry, what I was getting at there. Okay, so at least 2 days. This is part C, at least 2 days. So this is a building block. Okay, we're going to sort of use this shortly, this part here, a building block. Okay, so at least 2 days is probability of x greater than or equal to 2. Sorry, that should be a 2 there. Okay, so rather than going through the whole week, 0 or 2, 3, 4, 5, and 6, again, what we can do is use the complement rule. Okay, so more or less the same way. What is the complement of 2 or more? It is probability of 0 or the probability of 1 plus the probability of 1. So essentially what we're doing is using the complement rule. We had 0.7483 previously, and in the just up above we have 0.3720. That's the probability of x equals 0 and x equals 1 respectively. Add them together, that is, and get the complement of that, and we get 0.1497. Okay, so that's the answer to part C. And then what is the probability that the child lucks out, gets a prize every day of the week? It's not impossible, but it's very improbable. How improbable? Well, 7 choose 7, okay. So that will actually also end up as 1, okay. 0.1 to the power of 7, okay. And 0.9 to the power of 0, that's going to be automatically 1. So the answer is 0.1 to the power of 7, which is really 1 in, was that 1 in 10 million, I think? I'm not going to do it off the top of my head, but it's a really, really, really low number, okay? So if you're the child, don't tell the child that, you know, he's not going to win it every day, you know. So that's it. That's our binomial distribution question. And really the key thing there is back up above these parts here. Just knowing the formula, being comfortable with that formula, and also getting a bit of practice in with binomial coefficients. You get the hang of them pretty quickly, but I get that when you're starting out with them, they take a little bit of practice. So anyway, we'll leave it there.